Okay, Assalamualaikum and a very good afternoon to all of you. So today we are going to continue our lecture. I'm going to pre-record the lecture for the continuation of our chapter 6. So I'll share slides. So we stop at the second law thermodynamics regarding the refrigerator and the heat pump. Okay. The last one was causes statement. All right, I think this one. Okay, heat pump already. Okay, so we continue here. Okay, regarding the reversible and irreversible process. Okay, so what is a reversible process? So a process that can be reversed, okay, means that the state of our control volume or our case study or our object, our subject, can be reversed back to its initial state without any change in its condition. Okay, so it means that the process can be reversed. Okay, this is usually an ideal case, because we know in reality, this is mostly impossible to occur, to happen. It's impossible to have a process that is 100% reversible. Okay, means that it can be reversed back to its initial state. Okay, so that's why we have irreversible process, a process that is not reversible. Okay, so majority of the process exists in this world, it's irreversible. Okay, so for example, okay, all the processes occurring in nature are irreversible. So even though if we know that the process in this world, in the nature, are mostly irreversible, why are we still interested in reversible process, even though we know that DE is impossible to occur? Number one, why? Because they are easy to analyze. Okay, it's easy to analyze a reversible process, an ideal process. Number two, they serve as idealized models or theoretical limits to which actual process can be compared. So because we want to compare if without any friction, without any other issues or problem, how are our system, our heat engine, for example, our gas turbine, how are they going, what is the performance, the maximum performance, the theoretical limits that we call. Okay, so in order for us to compare, we need to have a baseline. So the baseline will be the reversible process or the idealized process models. Okay, so because we need to compare our actual process with a reference, so the reference must be the maximum possible performance, which is the theoretical limits, the idealized one. So in order to compare, we need to have this reference baseline, which is reversible process. Okay, so example of reversible process, for example, if you have a pendulum, a frictionless pendulum without any effect of wind involved, etc. So the pendulum can be reversed back to its initial state. Second one is quasi-equilibrium expansion and compression of a gas. Okay, so if we expand or compress the gas in the piston very slowly, then we might have a reversible process. Means that if we compress or expand the gas slowly, the change of the gas, the molecule or the heat, the temperature, pressure of the gas during the process might be reversible. Means the changes between its initial state to the final state can be similarly the same. So it can be reversed back if we do it slowly, okay, because equilibrium. So means that at each point, the process, the gas reach an equilibrium, nearly equilibrium state. So it is a reversible process. Okay, so we try to approximate reversible process. Why? Okay, so even though we know that most process in reality, in nature, are irreversible, we still need to consider the reversible process, the idealized process. This is why they are easy to analyze and they serve as theoretical limits. So how are we going to do that? How are we going to approximate the reversible process? So number one, we can imagine that the process is slow, just like the quasi-equilibrium just now. We conduct the process, the expansion or the compression, for example, we conduct the process slowly so that the fluid, the water or the gas is able to reach equilibrium, thermal equilibrium, etc. At each state. Maybe if we okay, for example, if the process involves between 10 minutes, okay, during the 10 minutes period of time, but maybe for each 10 seconds, okay, we slowly expand it, slowly compress it. So means that at each 10 seconds, its initial and final states during the small period of time are being conserved. Like so, it reached a thermal equilibrium for each state. So this process can be reversible. It's a very slow process. Otherwise, if the process is fast, irreversible, so maybe if we expand, if we push the piston, compress or expand it quickly, fast, so the change, the state of the gas or the water, the fluid inside the piston might change drastically, right? So example like this, if we again, if we throw our phone, right? We throw our phone, our handphone or cell phone to the floor. If we throw it drastically like that, so our phone might be broken. Okay, it cannot go back to its initial state. But if we slowly put down our phone to the floor, on the floor, so the phone is still okay, it's still fine, okay? It's still in its initial state because the process is slowly. So it can be, the phone can be reversed back to its initial state. It's still okay, it's still good, can be used, right? So that is example, reversible and irreversible process. So reversible process deliver the most and consume the least work. So like the phone just now, we slowly, so the work that we put, the energy that we put to slowly put down our phone on the floor, it's very minimal. If we throw drastically our phone, so it has to consume a bit of energy, right? Okay. So factors of irreversible process. So just now I explained slow expansion or compression of gas in the device with friction. Plus, if the process has a friction, so it is irreversible. Okay, the friction force can cause the irreversible process. So energy is used to overcome friction where the energy is lost as heat to surroundings. So to overcome the friction, we need energy. Okay, right. So energy is lost because to overcome the friction. So this energy loss means that the process is irreversible. Okay, the friction also exists between fluid solid and fluid molecules. So sometimes between two solids or two fluid and solids molecule also has some friction. And then fast expansion and compression just now, even though without friction, but the process is very fast, so it cannot be irreversible. It cannot be reversible, cannot be reversed back to its initial state. And then heat transfer through a finite temperature difference. So if the process is from is the same as the fast process, means the change is drastic from 20 degree to 30 degree. It's quite drastic. drastic, the change, the difference of temperature. Okay, so the condition of our fluid might change drastically. Okay, but if the heat transfer process is uh, during a very small period of time, so the process might be reversible. Okay, so in order to consider that the process is reversible, we need to divide the process into a small period of time. Means that when we want to analyze the process, we need to analyze it between a small period. We need to divide it between a small period of time, small zone. Okay, otherwise the change going to be drastic, so we cannot apply a steady state equilibrium uh, as assumption. Okay, so usually when we want to analyze the process, we're going to consider that the process is steady state equilibrium. So in order to assume that it is a steady state equilibrium, we try to divide the process into a certain small period of time or a certain zone, small zone. Okay, so that the process is reversible between the small zone, not the between its initial and final actual. Okay, and then internally and externally reversible process. Okay, this relates with boundary. Okay, so if we consider the boundary systems like the control volume I talked about previously. Okay, so we consider that the system within the boundary is irreversible or reversible. Okay, so means that the reversible, the term reversible or irreversible, it's within our thermal boundary that we consider. Okay, so for example, internally reversible process, if no irreversibilities occur within the boundaries of the system during the process. So for example, within the boundary, the pink dash line here, there is no irreversibility occur. So means that the system within the boundary is internally reversible. Okay, within the system. And then externally reversible if no irreversibilities occur outside the system boundaries. Okay, outside the boundary, there is no irreversibilities. Okay, and totally reversible process means internally and externally it is irreversible. It is reversible, sorry. This means that we define our boundaries. Okay, so within the boundaries, we analyze our system within the boundaries that we have defined. Okay. So a totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi equilibrium changes, and no friction or other dissipative effects. Means we consider within the boundary, we consider it is like an ideal reversible process. Okay, usually we will do this. We will do assumption like this. A